Welcome back to our series on statistical methods. I'm Mark Ledbetter, and we are going to cover the Chapter 4 code for, I need to change this to a randomized complete block design ANOVA. Okay, and let's see, today's date is actually 4/7. So this is the type of thing, only this is what you should only change, this information. The rest of this header includes output. You need to leave that alone, and it needs to be in your file. So you definitely need to use this one. The good thing is I'm only releasing this version of this file, so we shouldn't have an issue. Okay, I've made some changes to help keep the figures where they're supposed to be in the plots and all that. Okay. So we've got our first chunk here, the options, and it minimizes my console, so I'm going to undo that. And then we'll run the second chunk. Again, you don't want to mess with these first two chunks. Okay, there's things in there that are quite advanced, and I'm doing this for you so that you don't have to. And then we have our example here. I will not read this. I hope you will pause and read this, but I want to keep the video short. There are 4 levels of extrusion or treatments, and there's 6 batches of the resin. These are our blocks that we're going to block out the effect of the raw material. Okay, and the order in which the extrusion pressures are tested within each block or each material is going to be random. Okay. Our response variable is yield. It's really important that you understand what the output is and what yield. That yield in this case is going to be our output variable, and then the PSI and the material are going to be our input variables. Okay, so I've copied this over from the data file. Actually, this problem isn't in there, but let's pretend that I did. I've lined it up. The first column is the random order. And then I have the extrusion pressure, then I have the batch of material, and then I have the actual yield and percentage. And so this has 4 columns, so I need to make sure 1, 2, 3, 4 that I change in col to 4, and then I need to have change the column names to make sure they match what exactly I have. So that's very important. And then the rest of this code, Y1 here you shouldn't change, and then Y2, what we're looking for is if there's an observation or an order, you don't want that in Y2. Y2 we're going to print out and make look pretty, and I've found that it's difficult to get rid of this this row here, this column here, when printing, so why not just, I made a new Y, which was without that column, and so now when I print, it's going to be pretty. Now, this is very important. The PSI, this 9100, that's not, we're not trying to use that as a number. We're using this as a factor, as a level of our variable. So we've got all these repeats, 8500, 8500, 8500. That means it's going to be a factor, okay? And then we've got 1 through 6, which is just a batch. It's just representing the batch. But the batch is not, 6 is not a better batch than 5 or higher or something. It's just 1, 2, 3, 4, 5, 6, and they were randomly chosen. So this is, this has random effects, okay? But we're not worried about those at this point. But so here we have we're making PSI a factor, and we're making batch a factor. Okay, they have to be a factor for Levine's test if you were using this for Levine's test, or the ANOVA in this case, for it to work correctly. Okay, and we could verify our levels of factor, like here's the PSI and here's the batch, and if it says null, then there's a problem. Okay. And then we're ordering Y0 and Y1 by the order. And this is important because if you want to do a graph by time, you have to have the observations in order, or else if you plot lines, those lines will go all over the graph and make it really messy. Okay. Then we're getting rid of our row names so that our tables don't have this 1, 2, 3, what have you, printed out. It's meaningless, so why have it there? Okay. A equals 4, this is something you have to change each time or verify that it's correct before you do that. Now, I've only made this good for a balanced design, so if it's unbalanced, then there would be a lot of work to do. So we're not going to worry about unbalanced designs in this course. This software can handle that, but I've done some automatic things like in row, I've calculated little n. Well, if little n is not the same all the time, then you'd want to comment this out, and anywhere it says n, you might make a vector of n1, n2, n3, and then again, it's going to be more complex, so we just didn't cover that. And then I've added this latex options equals hold position. That's important because it'll put your table where it's supposed to be now instead of letting it float around. And it was quite the pain to try to get this lined up with the table in the right spot. It'd float above where it was or way below. So now it should be in a good shape. Let's run this chunk. And of course, when you're running a chunk at a time, it's not an issue. It's when we knit. It's when we knit that becomes an issue. Okay. So here's our table, and it's ordered by these PSI, okay, and then by batch. Now we have our descriptive statistics. Again, if you don't have, if we don't ask you for point estimates or something, if it's not specifically asked in a homework problem, you could get rid of this section. If it's a project, you will keep this section. Everything will be in here, okay? Everything in this file will be done, basically. Almost everything. There may be some things when we get to the residual analysis that you don't need the extra test or the extra plots because it's obvious, or you may keep them so as a verification. So I've tried to make this as complete as possible. I want to point out that when we do our descriptive statistics here, you need to look at this. We're looking at the medians, and we're going to talk about the range of the medians. We find the lowest, we find the highest. And then in this case, we do PSI. 8,500 is less than 87, is less than 89. These are ordered. But if this was a batch of material that was randomly selected, then there'd be absolutely nothing about the order of it. We would just assign 1, 2, 3, 4, 5, 6, right? So we wouldn't look at, well, as the batch increases. No, we wouldn't say anything about that because they're random batches and they're just arbitrarily numbered 1 through 6. But these PSIs, these are actual values, pressures, pounds per square inch. So 9,100 is higher than 8,500, etc. So I can look at what happens as the PSI increases. Well, the median is going down. And look at the mean. The same thing in general is happening. Okay, that's not occurring with the standard deviation, but it is occurring with the means and the medians, and we need to say that. So what did I include here? I said the medians for each yield, they range between these two values, and the mean yields are between these two values. Then I say the highest mean and median are associated with 8,500 psi. Well, if the mean was associated with a different PSI, then the highest mean was with a different PSI than the highest median, then I'd have to make this two sentences and talk about the means, and then I'd come back and talk about the medians, or vice versa. So that's what I'm looking for, especially on the project, is for you to analyze this and say what's happening, okay? And I need to capitalize that. So both the means and medians decrease as the extrusion pressure increases. That's a key point here. And then the standard deviations range from this, and I put which PSI and to this. And you'll see that if you look at these values, they just kind of float around. So 8,900 is the lowest, then 87, and then this, and then this is the third, and then this is the fourth. So they're in no particular order here, okay, for the standard deviations. All right, you might actually expect it to be that the lower PSI would be either bigger variation. Yeah, I would expect the lower PSI to be a bigger variation, and I would expect the higher to be less, but that's not what happened here. Okay? So it decreased until we got to 8,900, and then it went crazy again. Okay, almost doubled. Well, 50% higher. Now, the exploratory graphical analysis, you really only need one of these. So you have to choose, or I will ask you for one of the methods. For the For the projects, choose which one you think tells the best story. So the box plots are here. Again, you know, everywhere you go, you're going to have to change these variables to match the names, right? And so one of the ways to do that is I hit Control F, Control plus F to find. You can also come up to Edit and Find, okay? And you can find, let's say, yield, and then you want to change it to something else. Then you type it in, and you can replace all of them right here. And everything will be changed over. So when you're changing variable names, that's an easy way to do it, is to use that find and replace. Okay, so here's the box plots, and I see pretty much the same thing. These bold lines are the medians, and they generally decrease. These two are really close to each other. Now look at the spread here. The spread of this one seems to be the largest, and that's what we saw with the standard deviation, that this one had the largest, and then 4 was real close behind it. And we're seeing, even though these aren't standard deviations, these are the IQR, interquartile ranges, this is the largest, this is the next largest. And then this happens to be the smallest. Also, I want you to tell me about the distributions. Well, if you rotated this 90 degrees, this side would be on the right, and it's bigger, so this means it's skewed to the right. Or if you want to think about a positive skew going up, this is positively skewed because the top side is bigger. And this one's positively skewed. This would be negatively skewed or skewed to the left, negatively skewed or skewed to the left. Okay? And then we have the dot plot. And we see that the general trend is going downward. Okay? And when we look at the spread in this, see, it doesn't tell us the standard deviation. It really, you're just looking at the range. You can notice the difference between these points and see that this will probably, even though the range is a little bit smaller than this one, the standard deviation was bigger by a little bit, and that's because of the distance between the points. Here, they're a little more evenly spread, but I'm going to talk about the range here because I can't do anything else with this plot. I can think about it, but I can't really measure it. I can just assess it a little bit. So what I'm going to do if I use a dot plot is I'm going to say, shows the downward trend in yield as extrusion pressure and PSI increases. Again, if these values were just, you know, cats, dogs, this, that, then you couldn't say that, okay? But in this case, they're meaningful numbers, so you can say it. And then I'm going to talk about the ranges. It appears that the range for 9100 psi is slightly larger than the others, but the difference is fairly small. If you notice, there's not a big difference. So this doesn't suggest that the equal variances has been violated, that assumption. But the standard deviation is difficult to determine if the assumption of common variances has been violated. So remember, the standard deviation is the variances, not standard deviation we're testing. So you would square these values and to see the variance. Of course, it is equivalent test that the standard deviations are equal. So I guess, but so here we're going from about 3 to 4.6 maybe. And if you squared this, it'd be about 9 to 20 something. So those variances, there's a bigger difference there, right? For the standard deviations, they look a lot closer together. Okay. So we have this, again, you'd only include one of those. Now we jump to our one-way ANOVA, and we're going to test for the equality of treatments, treatment effects for each level of the extrusion pressure. Okay, so I've used the name here. I didn't say PSI, right? I know it's extrusion pressure, so I'm going to say extrusion pressure. I just named the variable PSI because it's short and it's easy. But here, I'm going to use the word so that people know what I'm talking about. And then we have our hypothesis. I have the treatment effects in here equal to 0 for you. And tau I not equal to tau j for some I not equal to j at alpha equals 0.05 in the model. And I've given you the proper model here for the RCBD, randomized complete block design, mu plus tau I plus beta j plus epsilon ij. Here's I, 1, 2 dots to 4. Yes, it's just 3, but some of you may not know that the dots here, backslash dots, does that. And if you have more than 4, then obviously you might want to use the dots. And then we have j equals 1 2 dot 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 to 6, right? And the test statistic, let's run this so we see what we get. And so this is giving us an F value here of 8.107 and a P value that goes with it of 0.00192. Okay? And so we have 8.107, 3 and 15 degrees of freedom. If you end up with 1 degree of freedom here, you've got a problem, and you'll probably end up with 1 here too. That means you didn't make them factor levels, and those results are garbage. Okay, so you need to make sure that the PSI and the batch are both factor levels. That way you get the correct degrees of freedom here, all right, instead of just 1. All right, 3 and 15 corresponds to a p-value of 0.0019. So I always round to 4 decimal places. You could round to 3 decimal places, but it is standard in statistics to use 4 in a lot of places. So 3 is also common, but I have chosen 4. It gives me a little bit better feel when I get really small values. I can say 0.0001, less than 0.0001, and that gives somebody a real good idea of what's going on, how small the values are. Hence, there does exist sufficient evidence to support the claim that the treatment effect of the yield is different for at least one extrusion pressure at a 95% confidence level. The test was performed using a randomized complete block design with J equals 6, I'm sorry, not J, B. B equals 6 batches or blocks of material for each of the A equals 4 extrusion pressures. So I'm being specific so that the reader knows what has been done here. Okay, so they understand the results. Now, so you need to reword this. I want to make sure that you understand that this sentence is critical if you want credit, especially for a project. You need to do the conclusion. All of it's important, but you can't just say anything here. You need to use this format in the conclusion. Okay, so I expect that. Now, for the interpretation of F sub B, you'll notice I have an F value here. But this is useless. You can't use this P value here, or the F value, you can't really interpret the way that you did it for PSI. You can't say batch is significant, blah, blah. No. You can't assume normality for these batches, okay? So because you can't assume normality, you can't really say that this, the F distribution isn't really satisfied. Okay, so this p-value is kind of garbage, if you will. Okay, so you don't want to use that. But what we can do, we can still use this and get information, just not a hypothesis test. So recall that the analysis of the F-test for blocks is not meaningful and should not be used in an RCBD. I might actually leave this in a report to somebody just so somebody doesn't say, why didn't you interpret that? Does this mean the raw material, blah, blah, blah? No, this is a randomized complete block design and we cannot analyze this the same way. But we can see that the MS of beta here is more than 5 times, that's the F value, more than 5 times larger than the MSE. In other words, F of B equals 5.249. And this indicates that the material did have a large effect on the yield. Therefore, blocking the material significantly improved the precision of the test for the treatment effects, PSI, by removing the variation due to material from the MSE. Otherwise, your MSE would be this plus this, and you would have a falsely high F value that was not as meaningful, okay? So this is good to do when you see that your MSE is significant with respect to your residual mean square error. Okay, so if this was like 0.45, if it was just 0.45 compared to 733, and this value here is way less than 1, then I'd say, yeah, blocking didn't do anything to help us here. Okay, there wasn't much there's not much variation due to material. Okay, I hope that helps explain that. So we're going to check for the adequacy of the assumptions, or adequacy, model adequacy verification, or verification of assumptions. So the first thing is the equality of variance. We need to plot. So I'm coming all the way down here and I'm going to run some plots. So we need to look at this chart, and this chart. This chart should have a straight line. You can see the dotted line at 0. And you can see some little variation in this line from 0. Okay, so it's not quite straight, but it's not really bad. It doesn't go up always, and it doesn't go down the whole time, and it doesn't like dip. It doesn't have a good specific shape. Now, when we're looking at these fitted values, it's really hard to tell because we've got so few values here. But when we look at the general spread of the data here versus here, we don't see a funnel shape. We don't see much of a pattern to it. And it's hard to tell because we have this 1 point here, 1 point here, 1 point here, 1 point here. It's very difficult to tell if we have a difference in variances across here. But in general, I look at the spread here and the spread here, and it's a little different, but not a lot. Okay. Then we look at this scale. So the analysis of this has been typed up here. No obvious structure or pattern, no funnel shape. No one fitted value seems to have an obviously different spread. As far as we can tell, it's just really difficult. The red line deviates slightly from 0, but not significantly. It's not all over the place or in a pattern. The scale location plot, this one is a little more concerning when we look at it because we kind of have a general downward trend. That's a concern. But remember that what we've done here is we've taken the absolute value of the residual and then divided that by the standard deviation and then taken the square root. So we've really altered the scale of this thing. Not only have we standardized it, but we went a step further and we square rooted it. So it makes it really, it emphasizes differences here. Okay, so with this, I'd say, well, the downward trend kind of concerns me. Okay, so I'd want to do Levine's test just to make sure. All right, but remember what our box plots look like, or in our standard deviation: high, lower, lower for this, high, low, lower, and then larger all of a sudden. So so it's difficult to say. Okay, but I don't see a pattern. I don't see a funnel shape. So this doesn't concern me too much, but I don't like the line trending downward. And then finally we look at this, and now this, instead of fitted values, this is across the PSI values. And we can look at this, we can look at each batch, because this first value here is batch 1. Now I look at it and I compare it to the first value in the second. You know, that's batch 1. Here's batch 1. And here's batch 1. Okay? So there's some fluctuation. Then I look at batch 2. Let's see, which one is batch 2? Oh, it's taking, there we go. So I think this is number 2. And then this is number 2. So they're negative, and then positive, and then positive. Okay, so some switch there. And then look at the 6th one. Here's the 6th one right here where my mouse is. So that's really close to 0. This one's really close to 0. This one's right at 0. And this one's right at 0. So let's see what I've written about this. Okay, so this is the leverage plot. Again, there's no obvious pattern or structure. We did not see a dramatic change in the edge points across the levels. No one treatment, PSI, has a spread that seems significantly different from the others, or it's obviously different. When we look at each batch, we see that batch 6 residuals, that's the one I was just pointing out, are all very close to 0 for all 4 PSI levels. So it has significantly less variation than the other 5 batches. However, since it's only 1 out of 6, we will accept that the model assumptions are met. I'm going to verify that a little bit. I'm not going to test for the variations across the different batches, but I will test across the PSI. Okay? And we could test that. So what I did was I used Levine's test. It won't do both at once. Here's Levine's test. And so I get a 0.59. If I want to change this to batch, let's see what we get. BATCH. I still get a 0.377. So we could check this independently, each of them. And this will be PSI. Okay, so we're going to run this, and now we have two of them. So I've analyzed this one. I've put it up there, and let me find it. Quality of variances, here we go. Levine's test. So here's the first one. The hypothesis test is this against claims. And so I've done this all treatment PSI. So let me copy this and paste this, and then I'll say all batches, and batches, I don't need all, yeah, and I'll say material, in case anyone doesn't know that that's material, have a common variance against the claim that the batch variances are not equal at alpha equals 0.05 in the same model. The test is, now I have to change this value. So let's come down and find that value. 1.135237777, 5 and 18. And 5 and 18, because we've got 5 batches, okay, or 6 batches, so 5 minus 1. And then this was 0.3777. We do not reject the null hypothesis, and their capitalization seems to be a problem with me in this program. There does not exist sufficient evidence to support the claim that the assumption of equal variances for batches, and up here I should say variances for extrusion pressures has been violated at a 95% confidence level using this would be now this would be A equals 4 for each batch, observations from each batch of material. Okay, so when we're doing the treatment levels, there's 6 batches, each of those in this completely randomized complete block design. Each treatment has 1 batch associated with it, and each batch has the 4 different treatments. So here's the 4 different treatments. Each treatment has the 6 different batches. Each batch has the 4 different treatments. So we have to look at it there. So there are no violations of the assumption of equality of variances here. Okay, so we've proven that without a doubt with Levine's test by doing both of those tests. Now we need to look at the normality assumption. So when we look at this, this is pretty good, except I'm a little concerned about this area right here. If it was just these last 2 points, I would not be concerned, but this third from last one is a little concerning. So what I'm going to do is I'm going to come down, here we go, to this, and I'm going to plot the residuals. So I've got standardized residuals. This is the model residuals, SD model residuals. So I'm dividing by the standard deviation, and I'm doing the QQ plot of that. And I could change this to 4 and 4 at first just to see. And you'll notice I changed this, right? I have to change my model here so that it looks right. And right now I have it as figure 4 because I've got the dot plots and the box plots, but it would change to figure 3 if I took one of those out. So when I look at this, I've got one point that's right on the line, a little bit over. That's not great, and this point's on the line. That's not great, and it makes me wonder what my p-value would be here. And so I'm going to run, the Shapiro-Wilks test here, or Wilk test, not Wilks. And again, I got a p-value of 0.3689. So normality has not really been violated, even though I have this one point that's almost an outlier, okay, and another point that's right on the border. But a lot of these points in the center are real close to the line, and look how narrow this 95% band is, okay. I could change this to 2 to 2, -2, and +2. and that's my y. And what happens is it gets harder to see what's going on. Well, with this point, it's the line, but you can definitely tell that it's well within. But it blows this up so you can see this a little bit better. I think I'd probably leave this at -3 to 3. So you can play with that limit just to make sure that you're capturing everything, and that looks better. I can see everything now. I can see the whole band and know that everything's okay. All right. So now we got to write it up. Have to write it up. So normality, most points lie close to the line. A few points in the upper half deviate somewhat from the line, but do not appear to be of concern. However, since we have some values, some values in the upper half of the QQ plot that depart from the line, we used 95% confidence bands, and I said figure 4, you'd have to change that to 3 once you remove either box plots or dot plots, right? To verify whether the normality assumption has been violated. So, and I didn't finish this, we have 1 point slightly outside the confidence bands and 1 point on the confidence band. We will perform a formal test for normality to verify. Verify, okay. The assumption. So, and then I've written that up. We test the hypothesis H0, the residuals, don't need capitalization here. The residuals are normally distributed against the claim H1. The residuals are not normally distributed at alpha equals 0.05 in the model. Again, I've given that to you for I equals. You'll have to change that if your levels change, and this number if the number of blocks change. The test statistic is here, corresponds to a p-value. We fail to reject the hypothesis of normality. There does not exist sufficient evidence to support the claim that the normality assumption has been violated at a 95% confidence level using a sample of n equals 24. Why? Because it's residual values in this case. Okay? Hence, there is no evidence that the assumption of normality has been violated. So we have definitive evidence that says we do not reject the null. Now we need to go on to the independence assumption, and we have to look at this in time. So here we come down to this plot, and maybe I should name this independence, so that when you see this you'll know what that is. And when we look at this plot, I've got 2 on this side, then 1, then 3 on this side, then 3 on this side, then 3 on this side, then 2, then 1, then 1, 2, 1, 1, 1, 1, okay, maybe 2, and 1. This is very up and down, random, so 3 in a row is just not enough to say that this is a run, okay? You need 4, 5 or 6 or something like that on each side, and a few of them to say, oh, independence has been violated. And the thing about this is that I randomly generated the order because I don't know it. So you know, any violation here in my mind, to report it, I would say, I mean, if you were a student and I give you this problem and you saw runs, then you'd say the assumption of independence has not been or may have been violated, and therefore the results may not be meaningful. Okay, so all the results. So it's a serious thing. So, but remember that in this case I'm just generating so you can get practice. Okay, so in Figure 5 there are no runs of positive, negative residuals to indicate a positive correlation. There's no evidence that the assumption of independence has been violated. In conclusion, all the model assumptions have not been violated and our model is acceptable. That means our analyses are acceptable. Okay. So then we come down to contrast. The first method is Sheffey's method that I'm going to cover. Then I'm going to cover Tukey's and and then the Bonferroni and LSD. I'm going to make this a lot less complicated than I did in chapter 3. So what we're doing, here's the comparisons for Sheffe. Okay, so you can change the confidence level if you want. Remember, and it says 95% family-wise or experiment-wise confidence level. Okay, and it does all possible pairwise. And then it gives you a p-value. None of these are less than 0.05, but look at this one. It's right at 0.05. It's got this dot here, and the dot is right here, and it says 0.1. Okay, nothing is between 0.1 and 1. A dot is between 0.05 and 0.1. And a star is between 0.1 and 0.05, you see, and the 2 stars between 0.01 and 0.1, and 3 between 0 and 0.001, okay? We only have the dot here. So this makes it nice that we can just quickly look down and see which one may be. This is really, sorry about the display there, this is really close to 0.05. And remember, I did all 6 of these pairs, so I'm data snooping. So it makes me think that this difference between 9100 and 8500 is significant, but because I looked at this, all of them, it's right on the border, okay? So what I did was I wrote this up as a hypothesis test, and so I've given you that. And then I said the difference in treatment effects between the 9100 psi and 8500 psi is, and I give you the estimate. Here's the value. Oops, sorry about my display. It's really acting up. Negative 7.05. Okay, and then I give you the p-value, which is significant, not at 0.05, but at 0.10. There does exist significant when it's that close. Remember that 0.05 is not some magical number. When it's really close to 0.05, you may want to say that at alpha equals 0.10, it is significant. Or you could say it's borderline significant at 0.05, okay? And I've written this up 90% experiment-wise confidence level, okay? And B equals 6 observations per extrusion pressure setting. Okay? No other differences in extrusion pressures result in a significant difference in yields. The borderline result is due to considering all possible pairwise contrast. If we investigate only 3 independent differences using a different method, the difference between 9100 and 8500 psi may be more significant. So let's do that. So we're going to use Tukey's method. Now it's looking at all the possible pairwise things, but remember it's a little less conservative than Sheffe, I think. So let's run Tukey's method down here. And now here are the differences for the PSI. And you'll see that this confidence interval here does not include 0, and this one here does not include 0. And this is not meaningful. This is including your batches. This is the difference in batches. This one here doesn't have 0, and this one here. But remember, that's not meaningful. So what we're looking for is this table that prints out. And so look at the p-values, and if you see anything below 0.05 or close to it, and we see these two. So with Tukey, we have 2 differences. This is 9100 and 8500. 9100 and 8700 are significant with Tukey's methods. So a little less conservative, and I've written this up. So here is the write-up for the hypothesis statement. I'll let you read that on your own. And this is for the results. So this is the hypothesis statement. Here are the results for the 9100 and 8500. And here's the 9100 and 8700. Okay, and no other differences are significant. And then if I ask you for a hypothesis test, you need this stuff up here. If I ask you for a confidence interval, this is the interpretation you need to give me. And again, if you don't give me there does exist this sentence here, you're not going to get credit for evaluating this. And the same thing for the confidence interval. You need to give me this sentence to get credit for it. Okay? So I'm hoping that helps you, and I interpreted both of them with that format. Okay? And then finally, custom contrast. Now this is the Fisher LSD, which is unadjusted, or the Bonferroni. And so this is a little more manual, but what I did was I only did the independent contrast here. So this is doing 1 with 4, 2 with 4, and 3 with 4, okay? So, and remember, they went down, so 4 minus 1 is going to be negative, and 4 minus 2 is going to be negative, and 4 minus 3 is going to be negative. But these are independent. So A minus 1 contrast. So this is one set of independent contrasts. So that means if I do the Fisher, it doesn't matter how many I do because I'm not controlling experiment-wise. So right now I have it set for Bonferroni. I have 3 contrasts up here. And so I set M equals to 3. If I want, and I've given you a note, if you want to do unadjusted, change it to 1. Okay? But that's a little dangerous. That's a little too, unless you're just doing one contrast of interest, then that's a little, you're being a little too liberal with your differences there. And so you don't have to change much. If you leave it at 3, then what you need to change, if you leave it at these, if you have 4 levels of A, then you wouldn't need to change this if you don't want to. But you would need to change the names of the differences. So here I have the different extrusion pressures, right? And so let's run this. Here we go. And so you can see down here, now if I don't have p-values, but if both numbers in the confidence interval are negative, it's significant at 0.05. And this is Bonferroni. I divided by 3, alpha over, let's see, 1 minus 2 alpha m over 1 minus alpha m over 2. So that's my Bonferroni if I divide by 3. Okay? And so we see that 9100 and 8500 are significant. Also, 9100 and 8700 are significant. Okay? But 89 and 91 are not significant. 0 is in there. Well, if I ask for a hypothesis test, how do I write this up without a p-value? Well, I still have my estimate here, the difference. So this is what we can do. We write it up. Here's the hypothesis statement, just like the others. And then the difference in treatment, and I say which two. Here's my estimate, negative 7.05, corresponding to a p-value, just less than 0.05. Not equal, just less than 0.05. Didn't mean to have the equal in there. And so that's the best I can do. I just know that it's less than 0.05 because 0 is not in the confidence interval. We reject H0. There does exist a significant difference in treatment means between the 9100 and 8500 extrusion pressures and a 95% experiment-wise confidence level using a sample of B equals 6 observations per extrusion pressure. And then I did the same for this one. No other differences are significant. Now, if I ask you to interpret a confidence interval, here's the write-up for that. And both of them in this case. I don't need both of these, 2 of these. Okay. Now, what if I want to change this? What if I want another contrast? I'm going to add C4, C1, comma, 1, comma, negative 1, comma, negative 1. Remember your values here have to add up to 0. Okay, so what is this doing? This is taking the average of the 85 and 8700 and comparing it to the 89 and 9100. Is there a difference? Okay, now I've got 4 here. I'm going to change M to 4. Now, if I want Bonferroni, now I don't have 3 names, I have 4 names. Those 3 are the same. I need to add another one. So I add the comma here, and then I hit enter, and I add the quotations, and I'm going to say 85 plus 87 minus 89 minus 91, because that's what I'm doing here. So instead of putting the hundreds, you could put the 100. Well, I guess I will. We'll just make it a little longer, but that's okay. Then we'll know what we're looking at. Now, I have to change something else. Where's my matrix? Here it is. In rows, this changes to 4 because I've got 4 contrast, not 3. And now instead of a C-bind of C1, 2, and 3, I need to add C4. Okay? So those are the changes that I make. If I add something here, then I need to add it here, and I need to change the in rows. And then I need to modify these names. For every problem, you'll need to modify all the names. In this case, I had to add one, so I hit a comma here, enter, and then I described the last one. And now everything else should work just fine. So we run it. Uh-oh. And it doesn't like the fact that I've got 4 of these things. Too many contrasts. With this method, I can't have 4, so I can have 3 or less. Let me get rid of the one that I didn't like. I'm going to get rid of C3. So that tells you right there we're going to have, so with this method, I didn't realize it did that. It doesn't like you to have too many of these. And in row, going to go back to 3. And now, yep, it'll let me. And it turns out, wow, I'm surprised, that this is all positive, so that means that the average of the lower 2 is different than the average of the upper 2. Okay, so we learned something here, and then we could write that up. All right, so I'm going to undo all of this, if it'll let me, until I don't have a C4. All right, that should be good. And make sure that I didn't, okay, yep. All right, so that's it for this video. So if you're doing a project, of course, you'd have to add the intro and you'd have to add the conclusion. I've already really written an introduction here for you. Let's see, this is just a description, but what we'd want to do is say, what are we trying to figure out? What is it that see, the engineer suggests that, or suspects that this may be the case, and blah, blah, blah. So we'd have to say, we're going to do, we're investigating the effect of 4 different levels of extrusion. Yeah, so we basically have a introduction here. The conclusion would conclude what we see. So we would summarize everything that we had found briefly, but we'd summarize it. All right. Please, if you have questions, come to office hours. I am happy to help you. I'm also happy to walk through code with you. So I hope you will take me up on that if you need it. And please take care of yourself. Stay safe, because we hope to see you here next time.